Hello, hello honors pre-calculus. I'm just doing a quick recording of modeling periodic trig phenomena. So we're going to go ahead and get started. I'm going to share screen and try to contain things onto screen share. So I'm hoping that you can see this. I'm using new technology today, so fingers crossed. All right, so hello, thanks for being here. Today, what we're going to do is use trig functions to model periodic phenomena. So we're going to start with an icebreaker. We'll do some notes, brain break, CFU, summary, and exit question. Okay, so your homework for week 4 and formative for week 4 will be due next Wednesday. So just be on the lookout for that. Okay, so the icebreaker we had in class was, what's the worst thing about virtual learning and what's the best thing about virtual learning? My kids said that the worst thing is that you can't play with your friends, and the best thing is the breaks. All right, so I just want to frame the learning about sinusoidal applications. There are a ton of them, tons of them. Tides, motion of springs, wheels, sunrise, sunset, rates of change of daylight, and we're going to look at a couple of them today. So, and then there's a little GIF just kind of showing how the unit circle and trig values are connected to sinusoidal functions. All right. So we're just going to go ahead and get right into it. Let's interpret a problem. So this is fake. I made this up. In Cambridge, Maryland, the depth of tide varies sinusoidally with time. The Chesapeake Bay low tide was measured at a depth of 10 feet at midnight. High tide is at noon, which is at a depth of 30 feet. So we're going to just sketch a graph of the scenario with T representing time since midnight and D of T representing the depth of the water. So you're welcome to pause and sketch on your own and see how it looks. But here's what the sketch looks like. So we've got at 12:30 is our maximum, right? So noon, the high tide is a depth of 30 feet. And then at midnight, we have a depth of 10 feet. And then this is a 24-hour cycle. So back to 10 at 24, okay? All right, so there's a little sketch. And now what we're gonna do is use that information to write an equation. So remember that you have all these parameters of trig, of sinusoidal function equations that we talked about a couple of classes ago. So we've got amplitude, which is half the height of the wave from the middle to the top. We've got B, which is the frequency, which is 2 pi over the period, how long it takes to complete a full wave. C is your horizontal translation. We call that phase shift. And D is your vertical translation. Sometimes we call that the midline. C and D are really always in any function that we see in this course. Really, C is that horizontal translation left and right, and then D is for the vertical translation up and down. And then when you're deciding between sine and cosine, so the way I always think about it is if your function starts in the middle of the height of the wave, so like starting at the midline, I would pick a sine function. Because remember, sine starts at the middle and then goes up or down based on that. If your function starts at the maximum or the minimum, I would pick a cosine model because remember, cosine starts at the max. Negative cosine would start at the minimum. Okay, so we'll just go ahead and write a little equation for this. So what I would say, this isn't really letting me annotate here, is you can see that your amplitude goes from, is 30 minus 20. So your amplitude would be 10. B would be 2 pi over 24. So that would be pi over 12 if we were simplifying. C, our phase shift, we don't really have one because I'm going to say let's pick a negative cosine function, and then we could just say that our phase shift is 0. And then D in the midline would be 20. So if I were writing my equation, I would say that it's D of T equals negative 10 cosine pi over 12 quantity X, close parentheses, and then plus 20 for my midline. All right, so here's a different example. The temperature of a certain city was measured starting January 1st. The high is 85 degrees Celsius, and the low is 45 degrees Celsius, and it was reached on January 8th. Sketch the graph, write an equation for the function, and then we're going to do use the equation to actually make some predictions or evaluate some problems. So after how many, what was it? C, what was the temperature after 100 days? And D, after how many days did the temperature first reach 65 degrees? And we're going to want to have a scientific calculator for this. And I'll show you why when we go over it. So since this is a video, I'm going to give you sort of the work for it. So we've sketched a graph here. We can see that the high was 85 degrees, the low was 45 degrees, and we start and end our graph at, or our wave at January 8th, okay? So we have everything that we need to write the function. We have our amplitude, which is 20, right? 85 minus 65. B would be 2 pi over 365 because we're dealing in days now. C, we're going to call that 8 because even though we start measuring January 1st, we're going to say January 8th is when the cosine wave starts. And then D, midline vertical shift would be at 65. So I'm going to pick a negative cosine because I start at the bottom and go all the way up and then back to where I started. So I'm going to say my temperature function T of T is negative 20 cosine 2 pi over 365, quantity x minus 8, and then plus 65 at the end for my midline. Okay. What was the temperature after 100 days? So I can just substitute that in, and you can just use this scientific calculator to make those calculations, or if you have a calculator, TI-80 for at home, you can do that. I would just make sure that you are working in radian mode. So sometimes if you click on the scientific calculator, there's degrees and then there's radians. So you want to make sure that you're in radian mode, right? So basically what I can just do is just type this expression and it will give me, it should give me a value. So let's try that. So we've got negative 20 cosine 2 pi over 365 times 100 minus 8 and then plus 65 at the end, and there you have it. So we've got 65.258, which is the same thing that we had on that other slide. Now, if you switch to degrees, it'd be a different answer. So do you see the problem? You want to make sure that if you're dealing in pi, you're working in radian mode. Okay, and then this D is a little bit tricky. It deals with inverse, which we're going to talk about a little bit in the lesson after this. So after how many days the temperature first reached 65 degrees? So that's when we're plugging 65 degrees in for basically your Y, for your dependent variable, for your big T of T. So 65 equals the expression that we wrote, okay? And we're solving for T. So we're just doing it bit by bit. So subtract 65 from both sides, we get 0. Divide negative 20 from both sides, we still get 0. So that's what we have here, 0 cosine of 2 pi over 365 times T minus 8. All right, so inverse cosine of 0 and inverse cosine of this expression, that's going to knock out the cosine on the right. It's going to kind of liberate the argument that is trapped in cosine right now. So inverse cosine is obviously the inverse operation for cosine. And this is why, again, we got the scientific calculator here. Let me clear this out. So inverse cosine, you can find that if you click function, okay? And then you can say inverse cosine of, go back to main, 0. Okay, so the inverse cosine of 0 is 1.571. So I'm going to go back to my slides. So 1.571 is going to be what this left side evaluates to. And then that's going to equal 2 pi over 365 times T minus 8. The rest of it is solving that you've seen before. Divide both sides of the equation by 2 pi over 365. I'll get 91.25 equals T minus 8. And then if I add 8 to both sides, I'll get that T is 99.25. So after about 99.25 days, that is when the temperature first reaches 365 days or 65 degrees. So one of the things to be kind of careful about when you do inverse cosine is that this is asking when the temperature first reaches 65 degrees. So the principal value you get for inverse cosine will be indeed, you know, right about here, right? So it'll be right about here. There's another place where you'll reach 65 degrees, which is over here. Okay, so just be mindful of the fact that, you know, you want to be careful and interpret the problem the way that it's written. So first reaches 65 degrees, you would want to pick this this value that appears first. So just be careful with that. Okay. Go ahead and pause the video, try this one. Changing rate of sunlight at Sligo Creek varies sinusoidally with time. It is 0 in December and June and reaches a max of 3 in March and a minimum of -3 in September. Sketch a graph, write an equation, find the rate of change, and then figure out after how many days the rate of change of sunlight first reach 1 minute per day. Go ahead and pause the video, try the problem, see what happens. Okay, so I'm assuming you've tried it, given it a whirl. So here's what it is. So the changing rate of sunlight at Sligo Creek varies sinusoidally with time. So we end up with, because we're starting at 0, or not yet, we're at 0 in December and June. We're gonna pick a sinusoidal function for this because we start at the midline. The midline is 0. We get up to a max of 3 in March. March is the 3rd month. And then we get back to our midline at 6 and then down to -3 in September, September being the 9th month, and then back to 0 at 12. Okay, so that's our graph. And then our equation for the function is 3, because that's our amplitude, sine of pi over 6, and then just x, because the midline is 0, phase shift is 0, so C and D are both 0. So the only thing we really need to transform from the parent sine function is our amplitude and our period or frequency. Okay, what is the rate of change of sunlight in May? So plug in 5 for little t there, and we end up with 1.5. Okay, and again, if you need to see that model, this would look like this. So we have 3 pi over 6, 3 times sine of pi over 6. Times 5 minus 3, because May is the 5th month. And that's, sorry, not 5 minus 3, just 5. So there we go. So we're at 1.5. Okay, so then lastly, approximately when did the rate of change of sunlight first reach 1 minute per day? So that's, again, substituting 1m for big R of t. That's the rate. Divide both sides by 3, inverse sine, and then divide both sides by pi over 6, and we get x equals 0.649. So you could say after 0.649 months, technically that answers the question. Or if you think, well, January has 31 days, so 0.649 or 64% of 31 is about 20 days. So you could say, well, after about 20 days in January. Okay. This is our brain break. Since you're watching this video on your own time, you probably don't need a brain break, but this is our Black History Month Spotlight, Dr. Gladys West. Dr. Gladys West is a mathematician whose work on the development of models were eventually incorporated into the Global Positioning System, or GPS, which you know and use probably a lot today. And she was inducted into the United States Air Force Hall of Fame in 2018. Okay. So the second half of class is really stressing the importance of being able to evaluate trig functions. We're going to have almost every day going forward at least a couple of minutes devoted to this, because for calculus, it is one of the most important skills to have, is to be able to evaluate trigonometric functions at certain values very efficiently. So I have this link for the unit circle, and I want you to try and think on your own for these 5 problems what the correct answer is. What's the cosine of pi over 2? What's the secant of pi? What's the cosecant of 13 pi over 6? What's the sine of negative 11 pi over 6? And then what's the cotangent of 540? So go ahead and pause. You can, this slide deck is in the modules, so you can look at it and get a sense of it if you'd like to. Okay, so I'm going to go ahead and go forward. Okay, so here's our unit circle chart. Pi over 2 is right up here, 90 degrees, 0, 1. So that cosine value will be 0, right? 0 over 1 will just be 0. Secant of pi, so down over here on the x-axis, secant is 1 over cosine, right? Or, r over x, if you want to think about it that way. So that's also -1. Cosecant of 13 pi over 6. So this is when I want you to start thinking about coterminal angles. So here's just plain old pi over 6. 13 pi over 6 would be coterminal with that. If you think about 13 pi over 6 minus 12 pi over 6, which is minus 2 pi, is pi over 6. So 13 pi over 6 is located in the exact same place as pi over 6. Okay, so cosecant is 1 over sine. Sine is 1 over 2. So cosecant would just be 2. Okay. Sine of negative 11 pi over 6. Remember, negative, we go clockwise around the around the circle. So we're going to end up right here at pi over 6 again. So the sine there is 1/2. And then cotangent of 540 degrees. So 540, think about this. 540 is 360 plus 180 degrees, right? So if you get a really big angle measure, you can just start subtracting 360 until you get something that's in the principal part of the unit circle. So that's a handy trick if you need it. Not a trick, but a strategy. So 540 minus 360 is 180. So that puts you right here. Cotangent, remember reciprocal of tangent. So cotangent's x over y. So -1 over 0 would be undefined. Okay, so we're going to have little checks for understanding periodically that are graded. And so we're going to I want to make sure that you get a lot of practice with this and a lot of proficiency, because it's one of the most important things you can access for calculus, is just being able to evaluate that pretty fluently. So here's a CFU. If you missed it, email me and I'll give you another one. But the idea is to evaluate, leave everything as an exact value. Please don't round. And these are the 5 problems. Okay. Okay, so in summary, sinusoidal applications are everywhere, and we can use math to model them and make predictions. This was the exit question. So this was in paired X. So you would drag the red heart to the equation that models this scenario, orange heart to the equation that models this scenario, and yellow heart to the equation that models the last scenario. So since you're watching the video, this wouldn't be something you'd be able to do here, but maybe you can match it, sort of thinking about it in your mind. Okay. All right. So thank you so much for watching. I appreciate your time. Always email me if you have any questions, and have a great rest of your day.